All right, so we have been talking about function operations. And we talked about our four main ones, which are addition, subtraction, multiplication, and division. However, we do have another type, which is called our composition function. Again, we should have seen this in Algebra 2, but again, we're going to try and kind of put us all on the same page just to make sure that we all know what's going on. So the definition of a composition of two functions is basically we're going to be plugging in one function into the other function. So I like to call this the turducken. So a turducken is a duck inside of a chicken inside of a turkey. Some of us may have had this before on Thanksgiving, or maybe not, that's okay. However, I like to use this example because our duck on the inside is like our x values. Okay, our chicken is like our g of x values, and then our turkey is like our f of x values. Basically, we're taking our x values, sticking them into our g, and then we're taking those g of x values and sticking them into our f of x. We can also kind of look at it this way with like our bubble chart. I'm taking these x's, which are the domain of g, plugging them into g of x. And then my outputs for my g of x are also going to be the inputs for my f. So I end up with f of g of x. So let's look at some examples. So it says given f of x equals x plus 2 and g of x equals x minus x squared, find the following: f composite g of x, g composite f of x, and g composite f of negative 2. So notice that this symbol is a composite symbol. It is not a multiplication symbol. And that's a really big deal because a lot of these students will get those mixed up. And some of that comes from the fact that the symbols look really similar, and some of that comes from the fact that we just never quite learned the concept of composite, so we just assume or go with multiplication because we know that one. But be careful, this is different than multiplication. So I have f composite g. And from our previous page and the definition, I know that f composite g is equal to f of g of x. And they tell me that g of x is 4 minus x squared. And now this problem should look pretty similar. It's going to be very similar to what we did when we first started our functions unit. We're plugging in 4 minus x squared in for f. So remember, it's kind of like copying and pasting. I'm going to take this 4 minus x squared, copy it, and then paste it anywhere that I have in x for my f of x. So instead of writing x, I'm going to write 4 minus x squared. And then I'm going to add in the plus 2. So then simplifying, I get negative x squared plus 6. Now let's do it the other way. I have g composite f this time. And so again, we can rewrite that as g of f of x. We always want to start from the inside and work our way out. So we want to plug in our f of x, which is x plus 2. And then again, it's like copying and pasting. I'm taking this x plus 2. I'm going to paste it anywhere that I have an x in my g. So I end up with 4 minus x plus 2 quantity squared. Hopefully we remember that quantity squared means that I cannot distribute that squared. I do have to multiply it all out. So you end up with x squared plus 4x plus 4. And then I want to subtract. So we end up with negative x squared minus 4x. And it's important to note that we do not end up with the same thing. So our composite functions are not commutative. I can't do them either way. My composite function, the order matters. And that's going to be important. So for our last one, we have g composite f of negative 2. And we could do this one of two ways. We could take that negative 2, plug it into f, and then whatever we get out, we could plug then that into g. Or since we've already found g composite f of x, we can also just plug it straight into that equation now instead. So we have negative 2 squared minus 4 times negative 2. Negative 2 squared gives us 4, but then we have an extra negative there on the outside, and then we have plus 8. So we get 4 as the answer there. Also notice that if I had just taken that negative 2 into my f would be negative 2 plus 2, which is 0. Plugging then 0 into g, I get 4 minus 0, which is also 4. So like I said, we get the same thing no matter which way we do it. Alright, so next up, it says to find the domain for the functions given by f of x equals x squared minus 9 and g of x equals the square root of 9 minus x squared. So the first thing that we need to do is we need to actually find f composite g of x. So they give us g of x as the square root of 9 minus x squared, and we're going to plug that in anywhere that we have an x. So I have the square root of 9 minus x squared minus 9. Now, notice that when we square our square root, we'll end up with 9 minus x squared minus 9. So we just end up with a negative x squared. And if we were to just look at our negative x squared, we would say, oh, we're done. We don't have any domain restrictions. My answers is all real numbers. However, remember with our function operations, it's going to be very similar. I'm combining two different functions. So that means that if it was a restriction for my domain on my first one, it's going to have to be a restriction for the domain of my overall function. And my x squared minus 9 doesn't have any domain restrictions. However, notice that the square root of 9 minus x squared does have some domain restrictions. And hopefully we recall from our previous lesson that should look really similar. I have 9 minus x squared. So that means that my 9 minus x squared has to be greater than or equal to 0. Again, we have a nonlinear inequality. So we're needing to set that greater than or equal to 0. Except this time, we're not adding in the combined factor of it being a fraction. We just have to worry about the 9 minus x squared. So remember, we said that our first step is to first find the critical values. So we're going to set it equal to 0. Then we want to solve for x. So we get plus or minus 3 as our answer. Then we want to make that number line like we did before and place our two values on there. Once we've done that, we want to choose some values that are in each of our portions of our line that we now have. So I'm going to plug in negative 4 first. So notice I have 9 minus negative 4 squared is greater than or equal to 0. Negative 4 squared gives us 16. 9 minus 16 gives us negative 7. So notice that that does not work. Next up, I plug in 0. I get 9 minus 0 squared is greater than or equal to 0. Well, that gives us 9 is greater than or equal to 0. That does indeed work. And then lastly, we want to plug in just our 4. We'll notice that we're going to get the same thing that we got the first time, and that ends up with a false statement. So the only portion of our graph that's going to work is that middle section. We do still have an equal to bar, which means that we do filled in circles for those. And that means that the domain is going to be from negative 3 to 3. And since we didn't have any restrictions for our f of x, and we don't have any restrictions for our negative x squared, we know that this right here is going to be our overall domain. And so that would be our answer. So the big key to remember when you're finding domains of our composite functions is that if we have restrictions for either one of our original functions, it's also going to be a restriction for our combined function as well. Alright, so it says for each pair of functions, find f composite g and g composite f, and then state the domain and the range for each composed function. So for our f composite g, we're wanting to start off with, so f composite g of x, I'm going to start from the outside, or sorry, from the inside and work my way up. So I'm going to plug in g of x, and then I'm going to plug that in to my f. So I get 2 times 4a minus 5, so I get 8a minus 5. Going the opposite direction, we want to find g composite f of x. Again, working our way from the inside out. We have g of 2a minus 5. We want to plug that in now to our g. So we get 4 times 2a minus 5. So we get 8a minus 20. Now, hopefully we notice that I started with 2 linear lines, but we also ended with 2 linear lines. So when we want to look at these restrictions, we want to keep in mind our original restrictions. But since all of those are polynomials, we will not have any domain restrictions. So that tells us that our overall function is also not going to have any restrictions. And then I'm not super worried about the range. I mostly wanted to focus on the domain. So we've been taking functions and making composites out of them. Sometimes we'll also need to go the other direction. We'll need to take a function and be able to break it apart into 2 composite functions. So I have h of x, and I'm wanting to rewrite it so that I have 2 functions that when I plug in g of x into f of x, I end up with h of x. So let's look at what I mean by that. So notice that if I let my f of x equal 1 divided by x, and I wanted to end up with my h of x, notice that if we let g of x be x minus 2 quantity squared, when we plug this g of x into f of x, we end up with h of x. So notice that we could also do f of x equals 1 divided by x squared, which means that we could let g of x just be x minus 2. Also realize, some of us might have noticed, if we just let either one of these be our identity function, that is always going to work. However, when we ask it on a test, we will say list out options besides the identity function. So you will need to be able to at least give me a couple of other ones besides just plugging all of this into x or plugging x into x, because you end up with the same thing. Alright. On our next one, again, I want us to find some examples of how to break this apart. So if I'm wanting for f of g of x to give me h of x, notice that we could take f of x could be x to the third, g of x So it would be 1 minus x. We could also have f of x equal x to the negative third, and g of x could equal 1 minus x to the negative third. Again, those are just a couple of options. There's going to be multiple options. So as long as the two functions that you pick work, then that's fine. That can be an answer. So again, looking for two functions that when I compose them, I end up with h of x. So we can take f of x, let that be 4 minus x, and then g of x would be 5x plus 2 quantity squared. We could also take f of x, let that be 4 divided by x squared, then g of x would just be 5x plus 2. We can also throw in some negatives or fractions and things like that, but those are probably going to be the two more straightforward ones. So again, I'm probably just going to ask for like 1 or 2 examples. And so as long as we don't use that identity function, then we're